Welcome to week 7, Earth, Space and Biological Sciences. This week we're talking about digital approaches to learning, and we've got quite a bit to say, so we won't languish too long on the warm-up, other than to say that the tutoring and lecturing team in the course are working pretty hard at the moment to try and get your grades marked and back to you for assessment task 1. So bear with us while that happens, because at this particular point in time we have about 1/3 of the students in this subject who have yet to submit due to Cyclone Debbie constraints. So we just ask for your patience on that, and we'll keep you informed as we move along. So let's have a look what's happening in digital science. Okay, so the future of science is shaped by changing scientific practices. Not new. Goes back to the work of Thomas Kuhn, and we can see that demands expectations of students and also of political bodies, the Australian curriculum in 2012. And science is being brought into the real world. So much so that, as our little cartoon shows here, that there's no longer an apple for the teacher, just a Woolworths internet shopping account crediting one apple for one teacher. So we can be quite innovative in our interpretation of that. But this week we're looking at the ICTs, the internet, mobile and social computing, and seeing how they connect with science education to lead to more authentic scientific connections and curricula in the world. And of course the challenge here is purposeful learning. How do teachers create purposeful learning? In the past, science has been the teacher standing at the front of the class for 1 hour per week, talking about science as the sage on the stage, and students either buying in or buying out, depending on their level of interest and engagement. The whole purpose of this week is to show that technology can reduce the risk of disengagement. And that's really what we're trying to show. So at the end of the week, describe the purpose of science learning. Something you should know by now. We're into week 7. Explain the future of science in schools. You should have some indication that technology is going to have a big part of this. And discuss teaching strategies that can be used to improve science learning. And again, obviously, some of these will be the focus of your final assessment task in this unit, assessment task 2. When we look at the key terms, authentic learning, Bowd coined the term authentic learning in 1998. Learning that focuses on the real world, complex problems, encourages methods and ways of thinking used by practitioners. And this goes back to Piaget, 1946, 1962, who coined the term the child as a scientist. So it's the child as a scientist is the practitioner. That's what we're gearing our curriculum on. Mark Prensky in 2005 wrote about the digital native and students who've grown up with ICTs. As distinct to digital immigrants like myself, who had to learn and be dragged kicking and screaming, in a Buddhist sense suffering daily for their uptake of ICTs. Project-based learning, often known also as problem-based learning, is part of this week's constructor as well, and it's also about reality-based contexts. Social-based learning talks about collaboration, and the model I prefer to use here is that by Betty Collis out of Holland, who writes about the contributing student model, that every student starts off in the course as a learner but ultimately finishes up as a co-constructor of learning. And so social-based learning has got its emphasis very much in the work of Abraham Maslow, but also more recently Betty Collis did a lot of work around 2000, 2003, 2007, and she really has set the world standard in social-based learning. Untethered learning, we turn here to a guy called George Siemens, 2005. Technology-enabled learning basically says that even though you're teaching kids in the classroom now, in a year from now they'll be in a different classroom, in 10 years they'll be in a different classroom, 10 years from that they'll be in a workplace. These places are related. So learning is now untethered. Science is not confined to a classroom, and we can no longer see the teacher as the co-owner of science. It's now the internet, technology. The teacher has become codependent, if you like, on technology for their relevance in the world of science. A little diagram to demonstrate this. Now, here we've got a 3D diagram. You notice we're all very familiar with vertical and horizontal axes. We've now also got a third dimension axis here called authenticity of learning. So on the upright axis, we've got complexity, where we know, for instance, from our curriculum documents that we've got higher order thinking and we've got lower order thinking. We've got direct instruction, for instance, often espoused by the Cape York Institute and Noel Pearson, as being, you know, the best method for teaching Indigenous students. Well, that's actually a low-level pedagogy. That's down around here. It's very didactic, and it's all about drill and practice. So it's very low. If you really want to encourage learning and, you know, transformative learning, you know, transcending boundaries, learners growing and developing, then you need to move up this particular axis towards higher order learning. And you need to get away from didactic learning, where the teacher is the sage on the stage. When you get into coaching models, the teacher is the meddler in the middle, where they're sitting, you know, in the middle of a group of students doing small group work, you know, coaching, demonstrating. Ultimately, when you get up to constructivist models, Vygotsky's model, where you're actually looking, for instance, at, you know, the most capable other. Vygotsky talks here about, you know, how the zone of proximal development can be best negotiated by teacher and learner to lead to maximum teaching outcomes. And we can see as we go back in levels of authenticity, you know, you can come from the teacher at the front. We can look at integrated learning systems, you know, learning management systems, blogs, wikis, productivity tools. We can get students making videos, you know, making audio, doing a whole range of stuff, writing songs using wikis and blogs. We can get into a whole range of problem solving with real data sets. For instance, students as researchers, monitoring bird species, monitoring river and water quality, simulations, online. We can see here that as the task of science becomes more authentic, okay, it is moved, for instance, into the real world context and away from the artificial classroom. And the point I want to make here is this is an important continuum for you to understand. You know, before we move forward, we need to break the misconception that more technology equals more learning. Okay, because it's not the case. You can add a whole lot of technology to a course and, you know, you can actually destroy learning. It can be counterproductive. It's called the diminishing marginal returns. For every dollar in technology you add, you can get worse outcomes. Sometimes the best teaching is a combination of low-level pedagogies leading to higher-level pedagogies in a most efficient and effective way. So when we talk about teaching science, we're caught in a paradigmatic change. You know, Kuhn talks about this. We're moving from didacticism to transmission. So once upon a time, for instance, you know, the teacher at the stage stood at the front. Now, for instance, we're using technology to transmit learning to the learner. Now, in the past, students have been passive recipients. Teachers have simply presented the information. We're now looking at, you know, and this week's material is about how we can actually change this balance, how technology can present information in a more dynamic way through the use of multimedia. So much so that computers can result in more learning. TPAC, Technological Pedagogical Content Knowledge. You can see it's that little green section in the Venn diagram here, the interaction. And it's an interaction of technological knowledge of the teacher, the content knowledge of the teacher, and the pedagogical knowledge of the teacher. Now, unfortunately, teachers generally in the primary school and early childhood school are, you know, once upon a time you would study in this course, you would study 2 units of science, earth and space and biological. Now it's actually condensed into one. So you know, theoretically, you're getting half the curriculum time. Your technological science, you're getting, you know, one method in generic technologies. And your pedagogical science, you know, you're being coached and taught quite strongly in the pedagogy of teaching primary and early childhood. So we can see here that, you know, your technological skills, your content knowledge and your pedagogical knowledge may not be even. And the balance between them may not be even. So this green space in this diagram looks nice and even. But in fact, your technology might be quite low, your content knowledge may not be as strong as your pedagogical knowledge, and you may finish up, for instance, with quite a different looking space here. If that's the case, then you've got what we call the professional development challenge to take up. Toolishness is foolishness. Okay, little diagram on the side, we make sure every student has every possible new tool, and that does happen in at least 3 schools I know around Townsville, 3 private schools. They've all got the tools, but unfortunately, their students don't have much clue on how to use them. And unfortunately still, nor do their teachers. So let's try and avoid that. Colin Lancashire, who supervised my PhD, a lovely guy, Colin, his wife, Michelle Noble, they're prolific in their research about technology. And they argue that curriculum or pedagogy must not be hostage to technological change at the level of artefacts. In other words, you shouldn't be using technology instruments or tools above pedagogy. So, a robot, a computer, a piece of software, a digital microscope should not take emphasis above over the reason why we use those robots, that software, or that digital microscope. Technology can be a useful tool. We can use it to enhance teaching and learning, and one such way is through communication. Now, we don't all have to be technology experts. That's the great message here. We don't need to be technology experts. All we need to do is learn how to facilitate communication. When we use technology, often the teacher talks to the computer and the computer talks to the student. The student in turn then will talk back to the computer, which the teacher will then assess. And somewhere in between, we assume that there's been learning. Okay, there's an artefact of assessment and we mark it. Let's take a step back. As a concept, teaching hangs on the notion that information is not only transmitted but also received, and to a certain extent that it's understood. But how do we know something's been received and understood? The only way we know is by interaction. The same way as Vygotsky said we should know. Being in the zone of proximal development, being with the more capable other or being the more capable other, and then interacting with the other person. So effective interaction is not just about moving a mouse or answering questions. It's about teaching. Teaching in that digital environment. Table 9.4 is a heady one. I'm not going to spend too much time on it because you've got it in your textbook and you can read the background to it. But what it says is that effective science teaching and learning requires that students do the following. And we know those words because they're all transitive and they come from our curriculum document, the ACS, the F to 10 framework. We know that some of this stuff can be done class-based because we know science from a traditional classroom perspective. We also know that we can extend it to online environments. And here, Gregson makes some suggestions about how that extension might look. Everything from linking into online projects through to, for instance, use of webcams, interviews, primary sources, virtual excursions, right through to consulting with experts and project sharing and project management. The whole notion here is social and collaborative. What we're saying here, and think back to that 3D model I gave you, we are moving from one-to-one direct instruction through to an environment where the students are co-constructing their learners. They're co-constructing science from the real world and from the what matters perspective, what matters to them. And this is why this is a useful table, because we're not talking here about a list of things to do. We're talking here about a strategy for moving from science teaching, the science curriculum in the left-hand column, through to the collaborative and inquiry framework in the right-hand column. Spend some time looking at this, please. It's the most valuable document you look at over the next couple of weeks. Robotics is an example of that. For instance, I've been heavily involved in robotics probably for the best part of 10 years, including setting up competitions throughout Asia and Australia and the Asia Pacific. And with Brandeis University, we undertook some research to see what impact our robotics program was having around the world. And we can see here, for instance, that down here the robot is an artefact, just like a test tube. But it's a much more dynamic artefact because you can set it to work, you can get it to problem solve, you can get it, for instance, and I'm not joking, you can get it to save the world, you can get it to come up with real life situated environmental solutions, nanotechnology solutions, anything the imagination. It's limited by the imagination. Kids compete in teams. They do research projects in their local community. And over here, ultimately, they're rewarded for what we call gracious professionalism, that is for working together. So when we look at robotics, here are some of the amazing outcomes from this program we ran. According to the mainstream, 53% of kids will go on to attend university. Kids who come through the first LEGO League robotics program, it's up to 88%. 77% of those will go on to postgraduate education versus 63% of normal students. 55% will major in science or engineering, and 41%, and here's the interesting thing, of girls will specifically major in engineering versus 13% in the mainstream. So this gives you an indication of how valuable STEM or STEAM or science education can be in creating social opportunity, how dynamic and powerful technology is as part of the science curriculum. So effective interaction is about the communication of thinking and learning processes. And teachers can be most effective when they're getting students to reflect, discuss, take leadership roles, mentor, coaching, or as Bloom would say, problem solve, analysis, synthesis and evaluation. So we need to come up with technology solutions that are going to enable these processes. And once we do that, we are moving towards deeply contextualised and individually unique interactions. Okay, in other words, deep pedagogies. So why drive this? Beamish in Hour, have a look at the year, 1995, so 22 years ago. We knew it then, the educational value of technology does not lie in the computer nor in software, but rather in the processes of learning and teaching. In other words, in the provision of metacognitive experience, teacher instruction and cooperation among learners. Now, the Australian curriculum creates generic capabilities, and you can see one of those is ICTs. Okay, the ICTs, every student must be capable in the realm of ICTs, and that goes, for you as a science teacher. So there is a curriculum obligation when you're assessed on your placements. Your teachers will be looking for your use of ICTs, but not only your use, but also the use of your students. How are students using it to write back to you? So when we look at ICTs, we can investigate, we can create, and we can communicate with ICTs. And that means locating information, scientific information, resolving questions, challenges, critically analysing any trends, and presenting and representing their learner. And have a look at this, co-constructing knowledge. So your students are required to move not only from the passive recipients of technology, where you, the teacher, are using technology to bombard them, but they're actually required to pick up the technology and become producers of knowledge themselves. So in other words, you need to flip your classroom. You need to get your students researching, investigating and presenting scientific knowledge. And the best way to do that, I've found, with robotics is games. And I've introduced you to Crawford before. They are ancient, they're time-honoured. Every society has had its games, initiation, rituals. Okay, they are the original education technology. Do they have educational value? Of course they do. It's schools that are the ones we're proving difficult to support in a research sense, because some schools work, most schools don't. Games, however, all work. And it's a vital educational function for any creature capable of learning, says Crawford. And again, look at the date. That is over 40 years ago. We've known this for a very long time. Gregson goes on to talk about examples of ICTs that represent good pedagogy. And he's got mind mapping in there, kidspiration, data logging, digital microscopes, video cameras. Video cameras are a favourite of mine. Kids can do so much with video cameras. It really is very PRG, becoming scientists in their own world. Databases, spreadsheets, some great projects, students monitoring frog populations in various neighbourhoods, bird populations. In Cairns, minor birds were a huge population problem in terms of displacing species. So school kids all around Cairns were actually engaged in a joint project with JCU to monitor the numbers of the minor birds. Photo stories. You know, you may look at the birth of a species or a birth of a creature or the life cycle or you know, butterflies or butterfly food sources, a range of things you could look at. Sock puppets. It can be that simple. A sock puppet is a technology artefact. Now, an artefact can be as simple as a piece of string tied around your finger. Think about it. When you need to remember something, you tie a piece of thing or an elastic band is what I do around my finger. I don't remember what it was, but when I look at the elastic band, I think, why is that there? And all of a sudden it triggers the memory. It's an artefact. Blogs, wikis. Problem is, many blogs and wikis are used by teachers to spread their own information. It's just a surrogate for teaching. Think about how you can use a blog and a wiki to hand it over to students. Games, simulations, scientific applications. Those of you doing science in term 2, I'm actually going to ask you to purchase a phone app, and we're going to build a lot of our scientific and chemical inquiry around that. Augmented reality, 3Ds. Again, there are some very, very good computer games that do exist with real-world applications. But today's students are different, and today's educators typically have a content methodology focus, not an engagement focus, as we found from last week's content. But when we look, games produce learning with engagement. Kids want to learn with engagement all the time, and engagement is therefore more important than content. But kids hate the fact that we ignore this. So we've got to come up with technology that brings this into our framework. Prensky talks about digital immigrants, digital natives. And we can talk here about conventional learning speed, the curriculum documents. How often do we walk into a classroom where we've got kids that are moving so much faster than our curriculum? You know, kids work and connect at twitch speed. Our curriculum, you know, basically gets them working at snail pace. Our curriculum is step-by-step oriented, where, for instance, our kids, for instance, are looked at random access as their goal. You know, that they don't say, you know, for instance, teacher just will say, okay, well, today I'm going to, you know, show you this and tomorrow I'll show you that. Kids, you know, often want to see the whole of the moon before they can actually look at the parts. Linear processing versus parallel processing. My daughter's a doctor. I work on my computer with 3 windows open. She works with 7. She's constantly parallel processing so many different issues. I look for text first. Okay, digital natives look for graphics first. I'm very work-oriented. Okay, I need to do this because it's part of my work. Okay, digital natives, on the other hand, are very play-oriented. I've learned all of this because I've played in these environments. For a digital immigrant, for instance, I use standalone technologies. The digital natives, okay, very much connected. And the missing word here is, you know, from George Siemens' work, connectivism, which talks about being integrated into your work, into your life, into community societies. So, you know, very much so as a teacher, you will find you're standalone. You may have faculty to relate to. You may have peers. But your kids, for instance, are all on social media. You'll find that connectivism is huge and very, very strong. What do they learn? Well, here's a long list of things that they learn. Deductive reasoning, the use of symbols. You've got your traditional scientific thinking covered. Okay, you've got it all covered there. Plus, multitask processing, rule understanding, strategy, morality. And you get kids playing computer games. Half of the outcome, of course, of a computer game is to, you know, gain access to the higher levels. What is the result of the gaining access to the higher levels? Of course, world domination, but there's also a moral component to it. There's ethics involved in getting there. There's digital literacy, there's concentration, there's a whole range of social skills involved in using technologies. And here is the warrant, here is the caveat for learning and applying digital technology to science learning. You can actually produce a wide range of learning outcomes. Problem solving, use of symbols, academic skills, comprehension skills, knowledge transfer. all really, really viable scientific outcomes. Gregson tables these in table 9.4, and he uses basically the 5 E's, or the 8 POE steps: research, gather data, data analysis, construct explanations, present results, apply concepts, collaborate, and make connections. As you can see, that's basically the 5 E's. That is also POE, and that really is, the model for using online learning in the classroom. You can achieve what you can achieve in a face-to-face lesson with an online lesson, but this final point about making connections and collaborate with others, you can extend the classroom way beyond the physical limitations into networks of experts, into communities of practice and communities of scholars and scientists. The Centre for Educational Multimedia. Now, these are all hyperlinks and all about exemplar schools, digesteries of using innovative learning technologies. Have a look at them. They are definitely well worth a look, but they're all, fairly well-rehearsed steps now in terms of applications of ICTs to and digital technologies to science learning. You've got your virtual learning environments. Now, Queensland, Education Queensland doesn't use one of these. It's just too difficult. Too many schools have different levels of resources, so there's no VLE in schooling, and arguably it's not needed. A school can achieve a virtual learning environment simply with a shared file structure. So, Moodle is also cheap, it's free, and if you've got someone with the skills to grow and develop a Moodle, it can be a virtual learning environment too. Student-generated video, I'll talk about in a minute. Interactive whiteboards, I'll talk about. Digital resources, have a good look at those. And web quests are a fabulous tool, and not hard to put together. Create a blog or a wiki in Weebly, and you can actually set up the most brilliant web quest that is foolproof. And the nice thing about Weebly is it's free to your students, and you don't have to pay anything and you don't have to upgrade. It's there 24/7. TFF, Teaching Teachers for the Future. Now here's a sample lesson, 70 minutes long, and it breaks it down for you into the, okay, we've got to have an introduction session. Students have then got to get into choice of objects, and that's got to be informed choice. Metal munches is obviously the theme. There's a group work activity, and finally a culminating activity is a debrief involving the whole class. As you can see, it's broken down, starts at the whole class. The teacher takes over, the sage on the stage, then they become the meddler in the middle, and then it's the whole class again by way of conclusion. Digital learning objects, of course, they're posting on Glogster. Once that's been posted, I would say, for instance, beyond that, the class doesn't have to stop. Once you've actually posted in Glogster, you can then produce, for instance, or introduce external experts. Once the external experts have been introduced, you can then extend that classroom and that lesson indefinitely, getting those people to come in and comment on the learnings and feedback. Have a look at that one. Okay, obviously you're at a stage of your career where you're wanting to put together some practice lessons. When you go on placement, it's too late. You need to have a few up your sleeve already. So have a good look at this activity. Examples again, going back to Gregston. Okay, talks about some of these, productive pedagogies, but they're only productive if they're used in a sense where it gets students to become the producers or the co-constructors of knowledge. Okay, it's not something that the teacher does to the exclusion of students. Some of my favourite things, and I thought I'd throw this in. The interactive whiteboard. I like to talk about students as producers of digital knowledge, and this goes back to some of the stuff we were looking at back at the exemplars and Centre of Excellence. M-learning, e-learning, audio, video, data conferencing, and programming games. Let's have a look at some of them. The interactive whiteboard. I really like interactive whiteboards because here you can see it's touch sensitive. It's about the size of a board. And what it really does, it allows the teacher and the students to get away from behind a computer. So the computer is still a really valuable tool in the learning, but it's almost invisible, and that's the way it should be. Computer work is no longer hidden. Have a look at that picture. The teacher is standing off. I mean, she's still the sage on the stage, but actually she's probably more the meddler in the middle because she's between the technology and the learning. The kids are doing effective group work. We've got a student up on the board driving the inquiry. So this is very authentic, very student-placed, very contextual learning. Okay? And some of the advantages, they're listed there for you. It's no longer hidden. Out from behind the computer, strong visual cues. You know, and let's face it, most of us are visual learners, 60%. Procedural, task-oriented activities. For those of us who are not, you've actually got the guidelines. Group work, brainstorming, group decision-making, testing of group theory. Moving away from teachers as a locus of control. And you can also annotate and dynamically work with digital materials. So you can put up, here's theory number 1, here's our version number 1 solution. Okay, here's what happened when we tested it. Okay, here's what went wrong. Okay, here's our revised version. And the nice thing about a whiteboard is it prints out notes. So as a teacher, you've constantly got a record of what you did the lesson before. And that's important because often science can be taught a week apart. Digital video is powerful. And students, I think, can be really powerful producers, no matter what your discipline. Portfolio, and there I've written music. Science, you can write a science song. There's no problem with that. Get students to write a song about a major discovery or about environmental issues, protest songs, poetry, short films, all can be done with the students leading it. They can also be consumers that you as a teacher can actually lead the process. You can do theory, annotation, motion analysis, experiments, instructions, and that can apply across a range of disciplines. As a staff member, you're going to be in professional development. You're also going to be asked to do reflection and modelling, okay? And of course, a lot of that will be done via video and video instruction. For instance, go to the ACARA site. The entire ACARA site gives you instructions in video mode. Finally, when you converse with peers, if you're on a panel of moderation, you'll be doing video conferencing. So digital video is a powerful tool in the teacher's repertoire, also in a learner's repertoire. And bear in mind, if George Siemens is right, you are both a teacher and a learner. Okay, you're part of a learning community, and hence his argument, we're all connected, and we're connected in lifelong learning. Students as DV producers. This is the work of Shuck and Kearney. Now, this is a seminal piece. It's a really great piece of research, and they talk about students in the director's seat, tipping the classroom, and they look at the impact of digital video production on pedagogy. And what they say is, the more digital video production students do, the more their engagement and their learning is increased. And we look at teachers can use digital video too, and they can use it for content development. It also creates student independence because each student can access a video at their own rate. They can drive it as fast or as slow as they want. They can do it in peers or groups. They can discover things from video. And it's also authentic. Video is usually based in real-world contexts and relevant and produced by real audiences for real purposes. But then we introduce the whole notion of Vygotsky and his social constructivist learning. And we can actually look at Vygotsky's work and we can see just how important DV is. Sorry, don't mean domestic violence, digital video production. For instance, it creates the more capable other. When students make video, they become the more capable other. They have independence and they have ownership. It's collaborative because it's done as part of a group and class setting, and it's done usually in teams. It's problem-based and it's also authentic. So have a close consideration of digital video. It's a fabulous resource, and all you need is mobile phones, downloadable laptops, of course, where you can edit video editor, or digital cameras where you do video editing too. And of course, all of these make very, very productive pedagogies. So there are 3 modes of student production. They can do it to communicate, and it's something instructional, something to share. They can do it as an observation or analysis, where they can actually observe a phenomena and they can highlight their opinion or their analysis of that observation. Or they can do it after the fact. They can observe the phenomena and they can reflect on it. Now the research shows, and Shuck and Kearney again are very clear on this, that when we use digital video as an observation analysis tool, as a reflection tool, it's at its most powerful from a learner's perspective. And it's also the least common use that teachers give digital video. So it's something to think about. M-learning, mobile learning, is a favourite of mine. I remember at Griffith University I would lecture to classes of 600 people. How do you create interaction there? Well, technology, a program called Socratic. I would get the students to pull out their mobile phones. I'd get them to dial into the Socratic website where I'd set up a learning centre, and on my PowerPoint slideshow I would put up multiple choice questions, and they would enter their answer through their mobile phone, and my PowerPoint would reflect their real-time feelings or their real-time responses. So I would go through teaching concepts, and I would be able to assess a group of 600 people and how well they understood that as I was teaching it. Powerful tool. Think about it. And Socratic used to be the leader in that field. There are many, many options now. Wiki, write a science song. A wiki allows multiple people to work on the same information online. Bear in mind the only downfall is they can overwrite each other and you can lose it. But you can do a science encyclopedia, an encyclopedia of the environment, or an encyclopedia of a particular issue. You can write a song and create rules to a game or to a situation. A science lab, for instance. Forum is a role play. Now, last time I was in a classroom I was using Merapolis. Now there are better ones than this. You simply create 3 simple rules. Each person plays one part. You cannot kill another character, because believe me, it gets quite violent. And you cannot negate other characters' words. Okay, you have to actually go with the story. So in a situation like this, I mean, I would create a scientist, I would create an industry representative, and I would create, for instance, a student. And those 3 personas, the student would interview both the scientist and the industry person in this hypothetical forum. And what you have is you have basically a written, issues-based, authentic, contextual assessment. Think about it. It's not rocket science. Blogging. Blogs, okay, basically online journals. Too often when teachers use blogs, they do old people blogs. Okay, it's a little bit sad, a little bit didactic, a little bit controlling. You look at an old person's blog versus a young person's blog. A teacher's blog smells and looks and tastes like a teacher's blog, you know, try not to step in it. A student's blog looks and tastes and smells like a student's blog. The aim with blogging is to start off at a beginning point as a teacher and then to hand the blog over to learners so that they're actually producing their assessment and co-constructing their understandings. Audio, video, data conferencing, things I use every day, things I'd swear by, Skype. Google Docs. Create a Google document. Okay, it could be a spreadsheet, it could be related to bird species or river water quality. Dragon Easy Speaking. Okay, something I talk to my computer often and it just records my words. Messenger, Zoom, Jabber conferencing. Jabber's brilliant if you can use it in your school. Okay, because you can connect panels of experts to Jabber. And you can actually have an online chat with panels of experts interrogating some very, very influential people. I remember when I was doing the robotics, launching that up in Cairns, a scientist called Dean Kamen. Now, you all may know that little upright scooter structure, you know, the little one that's driven along on 2 wheels. I'm trying to think of the name right now, but I can't do it. But Dean Kamen invented that. George H. Bush, the father of George W., was the President of the United States. Now, George W. Bush actually started the robotics program or the robotics competition in the United States. Dean Kamen, who invented the Segway, actually, that's what it's called, also founded the first Lego League competition in the United States. And I had one other scientist from Russia, and I had the 3 of them online talking to a group of Year 9 students about the potential of robotics in the future and future careers. Can you imagine how powerful that was for those Year 9 students to be talking to an ex-president, to a leading American scientist and to a Russian scientist about applications of robotics? All made possible by Jabber. Assessment task 2. I'm going to start raising it and bring it into your focus, because even though we're still bogged down with the marking and you with some of you still finishing it, it's 2 parts. Part A, using professional literature, you've got to write a brief comparison of 2 alternate pedagogies for science teaching. Now there's a range of pedagogies. Think about which one you're going to use, but you've basically got to describe 2 different pedagogies. Part B, okay, 2 cards, but use 2 digital cards that could be used to scaffold independent learning in science by small groups of students in a primary classroom. Notice they're 2 cards. One card will relate to the early years, 0 to 3, the other to the upper years, 5 to 9. The cards should demonstrate a clear understanding of the pedagogy selected in Part A and use content from the 2 strands, biology and earth and space sciences. They must be in digital format. Now, what is digital format? Go and look at the website. Go and look at our course Moodle. There are examples. The card should cover a range of activities and include 1 card suitable for use in Prep to 3, 1 card for use in the 0 to 5, okay, for older learners, for the early childhood, people doing early childhood programs, or for years 7 to 9, people doing primary programs, okay, which scaffolds the use of an online science simulation. All right, so even though you're doing the early childhood and you may be teaching an early learning centre, you are going to have to find an online science simulation in the 0 to 5 age group, okay? So the pressure's on you to find that. 10 marks for your content knowledge, okay, will come from that. So a total of 40 marks. Part A is worth 10 marks. Part B is worth 40 marks. Assessment task 2, look at the example assessments on Moodle. Gregson 252 lists ideas. Gregson 257, 262 provides resources. Here are some online simulations to give you an idea of what we're talking about. So get on and have a look at those. Don't leave it to the last minute. And share your resources on the Q&A forum, please. Okay? Use your peers, share with your peers. That's what they're for. Summary of today's session. Toolishness is foolishness. Don't use technology unless it's got a real application. Technology can, however, facilitate better communication. And CMC, that's computer-mediated communication, can create much better learning. How you do that is through reflection. Reflection basically is metacognition. Through discussions, through having learners take leadership roles, through mentoring, coaching, problem solving, analysis, synthesis and evaluation. Those last 2 lines, of course, being Bloom's upper level taxonomical functions. Thank you for listening. I look forward to catch up with you.